Hello everyone, welcome to our deep reinforcement learning project. Our topic is optimizing electric vehicle charging with deep reinforcement learning. In this presentation, we will contain several parts like introduction, literature review, methodology, experiment, and conclusion. And now let me introduce further about our project. In this part, I will introduce the overview information of global climate and background of problems and challenges to the problem. Also, the brief introduction about deep reinforcement learning solutions and why we use it. Nowadays, climate change is an urgent problem to the world, like the global warming driven by greenhouse gases and vehicle emission are significant contributors of the issue. One of the proposed solutions is to build a sustainable and efficient transportation systems. The electric vehicles can be a solution. They can offer a clean alternative by reducing the tailpipe emissions and dependence on fossil fuels. The electric vehicles can also improve energy efficiency. However, transitioning to electric vehicle is not an easy work. The challenges like grid overload risks, energy inefficiencies, and needs for smart charging may make the transitioning tasks harder. So to better solving the tasks, we introduce a deep reinforcement solutions. It can make dynamic decisions in complex environments and is able to balance the competing emissions and the energy. Finally, our goal is to leverage the deep reinforcement learning to optimize the electric vehicle charging environment and ensuring the efficiency and the sustainability. Next, I'll pass it to Minhin to have a literature review. Thank you.
Hello, I'm Tomengin, and now I'm going to present about literature review. The optimization of electric vehicles charging has become a rising research area, providing innovative solutions to challenges such as grid management, cost efficiency, and renewable energy integration. A study suggests that electric vehicles offer significant value to electric utilities as power resource. For instance, vehicle-to-grid application is beneficial for system level, such as improved grid reliability, reduced costs, and enhanced integration of renewable energy resources. The findings show the potential of electric vehicles as an integral part of future sustainable energy ecosystem. A fundamental study provides a comprehensive review of electric vehicle technology, focusing on the challenges and opportunities of developing an efficient charging infrastructure. It has highlighted the key role of optimization strategy in promoting the electric vehicles. Based on these fundamental insights, a research proposed that adaptive charging network can be used. So this framework leverage model predictive control and distributed energy resources to optimize intelligent electric vehicle charging. The results show improved voltage stability and enhanced integration with distributed energy system, demonstrating a scalable cyber-physical approach to electric vehicle charging. The SustainGym benchmark provides reinforcement learning environment for sustainable development application, including electric vehicle charging. So this benchmark can be evaluating the efficiency of reinforcement learning model, making a significant contribution to the field. Together, this study highlights the transformative potential of deep reinforcement learning in optimizing electric vehicles. They address challenges such as grid stability, cost minimization, traffic management, and renewable energy integration, paving the way for a sustainable and smart transportation ecosystem. As the technique of deep reinforcement learning is growing, frameworks such as adaptive charging network and SustainGym are likely to play a key role in standardizing and accelerating the development of advanced electric vehicle charging solutions. That will be all for my part of literature review. My teammate will carry on.
Thank you, Minghin, and welcome to the methodology section for our presentation. In our methodology, we aim to develop a deep reinforcement learning framework for optimizing electric vehicle charging in a network. We employ an actor-critic approach with prioritized experience replay for efficient learning. The environment for training is derived from the SustainGym library, specifically the multi-agent EV charging environment. Let's delve into the details of how this is structured. The EV charging environment simulates real-world charging dynamics using the SustainGym library, which is based on the ACN Sim simulation tool. It models nonlinear battery charging and unbalanced three-phase power flows. The dataset includes 52 charging stations from the Caltech and JPL networks. The environment supports both single-agent and multi-agent settings, where each charging station acts as an agent, and the goal is to maximize energy delivery, minimize emissions, and stay within the power and network constraints. Now, let's break down the dynamics of the environment. First, the observation space includes components like time of day, remaining charging durations, energy demands, historical emission rates, and forecasted emission rates. This provides a complete snapshot of the system at any given time. Next, the action space determines how charging rates are controlled. Actions can be either discrete with predefined scaling factors or continuous normalized pilot signals that dictate charging rates. Finally, the reward function is critical. It balances three components: maximizing energy delivery, penalizing constraint violations, and minimizing carbon emissions. This ensures that the agent align with environmental and operational goals. So, to solve the EV charging problem, we adopt a deep reinforcement learning framework with an actor-critic architecture. The actor network maps the observed state to a continuous action, determining the pilot signals for the charging rates. Meanwhile, the critic networks evaluates the state by estimating its value. Both networks have four fully connected layers with value activation function and making them robust and adaptable to complex patterns in the data. Experience replay is a vital component of our methodology. The replay buffer stores transitions of state, actions, reward, and the next state. We use a prioritized sampling to ensure that the most informative transitions are replayed more frequently, and the priority of a transition is proportional to its temporal difference error, which measures the gap between the predicted and actual returns. We also use important sampling weights to correct bias introduced by prioritization, ensuring stable and unbiased learning. The training process follows a standard actor critic approach with temporal difference learning, and the critic network minimizes the squared error between the TD target and the predicted value. The TD target includes the immediate reward and the discounted value of the next state. The actor network uses the policy gradient method to improve its decision, guided by the TD error. To balance exploration and exploitation, we use an absolute greedy strategy where the exploration rate decays over time. So the training runs for a maximum of 900 episodes with models saved every 50 episodes to monitor the progress. So in conclusion, the DRL agent is trained to optimize charging decisions by continuously improving its policy over the 900 episodes. The final models are saved and evaluated to ensure robust performance under various scenarios. This methodology provides a scalable solution to manage EV charging efficiently while aligning with environmental goals. That concludes the methodology section. Now I will pass it on to Xintian for the experimental part. Thank you.
Thank you, Wei Heng. Hi, my name is Li Xintian. Now I'll present the results of our deep reinforcement learning framework for optimizing electric vehicle charging. Let's begin by outlining the hyperparameters and training setting. We use a discount factor of 0.99 and different learning rates for the actor and critic networks, set at 10 to the power of -4 and 5 multiplied by 10 to the power of -5 respectively. The batch size was 256 and we set the buffer capacity at 100,000 and epsilon decay at 0.995. The training was conducted over 900 episodes, each with a maximum of 200 steps, and we used the Caltech Summer 2021 environment for simulation. Now, let's have a look at the training outcome. As you can see in the figure, the reward trajectory can be broken into three phases. In the initial phase, the agent starts with low rewards and is exploring the environment and testing different actions. This high variability is typical during the exploration when the agent is unsure of the optimal strategy. Next, in the middle phase, the reward steadily increases as the agent refines its strategy, balancing exploration with exploitation of known successful actions. Finally, in the late phase, the reward plateaus, indicating that the agent has learned an optimal or near optimal policy and further training yields diminishing returns. Next, We compared the DRL method with the baseline approach. Both methods were tested under the same condition, with random seeds initialized from 1 to 123 for one episode each, ensuring consistency and fair comparison. The performance of each method is illustrated in the figure. The DRL method consistently outperforms the baseline across multiple test sets, achieving higher rewards, while the DRL method's reward distribution shows greater variability, with some peaks above 8. The baseline method is more stable but fails to reach higher rewards, peaking at around 4. Besides, the DRL method has an average reward of 3.46 compared to just 1.55 for the baseline. This shows that the DRL method can achieve higher rewards by exploring and exploiting the environment more effectively. In short, our DRL model significantly outperforms the baseline method in optimizing EV charging. The ability of DRL to balance exploration and exploitation allows it to adapt to dynamic environment and achieve higher rewards, thereby optimizing energy delivery and reducing carbon emission. However, there is some variability in the DRL rewards, especially during the early phases, which reflects the exploration-exploitation trade-off. Despite this, the overall performance shows that the DRL is a promising approach for EV charging optimization, particularly in complex or dynamic environments. Finally, while promising, our approach has some limitations. These include challenges with scaling to larger networks with hundreds or thousands of charging stations, the potential for varying performance in different real-world conditions, and assumption about uniform EV usage patterns that may not hold in all scenarios. That's all from me. Now, let's welcome Tauri for the conclusion.
Thanks, Xintian. And finally, I will move to conclude this project. Our key findings are that the electric vehicle charging systems can be effectively optimized by the deep reinforcement learning solutions in balancing and reducing carbon emissions. What's more, this project can make contributions to demonstrate the transformative potential of deep reinforcement learning in managing complex EV charging scenarios. Also, it can provide a scalable, intelligent solution for sustainable transportation systems. In the future, we aim to enhance our project with larger networks and incorporate real-time data and diverse grid conditions. Also, we aim to explore multi-objective optimization for broader applicability. That's all for our presentation. Thank you very much.